In the last two videos, we discussed the field properties and the order relation. But with just those two, there's nothing to distinguish the real numbers from the rational numbers. And yet, the rational numbers leave holes in the number line where it seems like a number should exist and yet doesn't. Let's look at an example of that. So, theorem, there's no rational number whose square is 2. Let's prove this. So we could assume for a contradiction that there does exist a rational number, say p over q, and we may as well assume it's in lowest terms, such that its square is equal to 2. We can multiply by q squared to get rid of the denominator. Well, since p squared equals 2q squared, p squared is even. But 2 is a prime, and so p has to also be even, because if p was odd, p squared would be odd. So we can write p is equal to 2k for an integer k, and subbing that back into the equation, we get 4k squared equals 2q squared. So 2k squared equals q squared, so q squared is also even, but by the same argument as before, that means q is even, and we've reached a contradiction, because we assumed that p over q was in lowest terms, and if both p and q are even, then they have a common factor, meaning they're not in lowest terms. And that means our original assumption was wrong, and so there's no rational number whose square is 2. This result was first discovered by the Pythagoreans around 500 BC, and it shattered the ancient Greek belief that all lengths could be expressed as ratios of whole numbers. Before this discovery, it was assumed that given any two line segments, there was always a third line segment whose length evenly divided both. However, considering the diagonal of a unit square, the Pythagorean theorem showed that this is not always true. Since the Pythagoreans identified numbers with rational numbers, they initially concluded that number itself was just a weaker concept than geometric length. But rather than abandoning arithmetic, modern mathematics resolves the limitation by expanding the concept of number with the axiom of completeness. What would go so wrong, though, if we just try to do calculus on the rational numbers? Well, because of the gaps that seem to be left, it would be super difficult to define concepts like continuity. So consider a bizarre function where we define f of x to be 0 if x squared is less than 2, and we define it to be 1 if x squared is greater than 2. Our graphical intuition says this should not be continuous, because it has a jump. But when we define continuity in the same way we will later on, but instead use the rational numbers as the underlying set, we would actually be forced to conclude this is continuous, because it has no discontinuities on the rational numbers. It's because of pathologies like this that we need to fill in those gaps. We need the axiom of completeness. So that we can properly state it, let's define two terms, upper bounds and lower bounds. Suppose we have a set A of real numbers. We'll say that a real number u is an upper bound for A if every element in the set is less than or equal to u. And we'll say that a real number L is a lower bound for A if every element in the set is greater than or equal to L. So let's look at a simple example. Consider the set 1, 2, 3. Then 3 is an upper bound, and so is 4, and so is 100. And something like 1 or 0 or negative 50 would all be lower bounds. Let's also define a supremum and infimum. So if A is a subset of the real numbers that's non-empty and bounded above, then we define the supremum of A, denoted SUP or sup A, to be the least upper bound of A. More formally, we would say that sup A equals S means S is an upper bound of A, and for every upper bound u of A, S is less than or equal to u. We define the infimum similarly as the greatest lower bound. So if inf A equals T, T is a lower bound of A, and for every lower bound L of A, T is greater than or equal to L. These are kind of generalizations of the idea of a maximum and a minimum, because the maximum of a set is an element of the set that's greater than or equal to every other element of the set, and that often doesn't exist. So consider the interval from 0 to 1, the open interval, not including 0, not including 1, but containing all real numbers strictly between 0 and 1. Doesn't have a maximum, doesn't have a minimum, but we would say that the supremum of A is 1, and infimum of A is 0, because there's no smaller upper bound, and there's no greater lower bound than 1 and 0. Now let's state our final axiom. Every non-empty subset A of the real numbers that is bounded above has a least upper bound in the reals. That is to say that the supremum of A exists and is a real number. The rational numbers don't satisfy this axiom. You could consider the set of all numbers whose square is less than 2, and that would not have a supremum in the rationals. We still will have to prove that the supremum of that set is in fact square root of 2. Let's state and prove a few more basic things about suprema and infima. The supremum of a set, if it exists, is unique. We can prove this by contradiction. So let's assume we have a set that has two different suprema. Let's call them A and B, and without loss of generality, we might as well assume A is less than B. Well, since B is a supremum, it's the least upper bound, meaning any real number less than it is not an upper bound. And so A is not an upper bound, which is a contradiction to A being a supremum. So the supremum has to be unique. Now you might wonder, do we need a similar axiom to the axiom of completeness for infima? Like maybe we need to assume that for every non-empty subset of real numbers that's bounded below, there exists an infimum in the reals? We don't actually need to assume this. We can take this as a theorem and prove it from the axiom of completeness just about suprema. So let's state this as a theorem. For our proof, we'll turn a question about infima into one about suprema. So let S be a subset of the reals that's non-empty and bounded below, and we need to show that this has an infimum in the reals. Let's define a new set, call it T, to be the set of negative x for each x in S. Now since S was non-empty, T is non-empty, and since S was bounded below, say it was bounded below by some real number m, well now negative m will be an upper bound for T. Because for all x in S, since m is less than or equal to x, negative x is less than or equal to negative m, so negative m is an upper bound for T. And since we have a set T that's non-empty and has an upper bound, we can say by the axiom of completeness, the set has a least upper bound. And so let's let S represent the sup of T. And now we can verify that negative S satisfies the definition of the infimum, and we know negative S is a real number because S is a real number. Since S is an upper bound for T, for all x in the set S, negative x is less than or equal to S, so negative S is less than or equal to x. So it is in fact a lower bound, but we need to show it's the greatest lower bound, which means if we take any small step upwards that it's not going to be a lower bound anymore. So let's let epsilon be greater than 0. That'll be our small step. And now we want this new number, negative S plus epsilon, to not be a lower bound for S anymore. So we need to find an element of S that's less than it. And so we can use the set T. Since S is the supremum of T, if we take a small step down of size epsilon to S minus epsilon, that's no longer an upper bound for T, which means that there exists an element in our set T greater than S minus epsilon. Let's call that element negative X so that we can negate things to find an element in S. Negating both sides and reversing the direction of the inequality, we can say that X is less than negative S plus epsilon. But X is in S because negative X is in T. And so we found an element of S that's less than negative S plus epsilon, which means negative S plus epsilon is not a lower bound for S. Now let's remember what we were trying to argue. We're trying to show that the set S has an infimum, specifically that negative S is the infimum of the set S. And we now have both parts of the proof, because we've shown that negative S is in fact a lower bound for the set S, and we've also now shown that if you take any small step upwards, that you'll no longer have a lower bound. What's key in this argument is that it works for all values of epsilon greater than 0. It works for epsilon equals 1 or 0.1 or 0.01 or any small positive number. So no real number greater than negative S can be a lower bound for our set. Thus, negative S is the infimum of the set S. This use of an arbitrary epsilon greater than 0 is a theme throughout real analysis that we'll continue to see. To show that the idea of a supremum and an infimum is a generalization of a maximum and a minimum, we might prove that if we have a maximum of a set, then that is equal to the supremum. If we have a subset of the real numbers that has a maximum, then the max of that set S is equal to the supremum of that set S. And if it has a minimum, then we would say that the minimum of that set S is equal to the infimum of that set S. So let's prove this. Suppose that M represents the max of our set, then M is an element of S, and for all other elements X and S, we have that X is less than or equal to M by the definition of M being a maximum. So M is an upper bound, And since M is an S, no smaller upper bound can exist, because then M would be greater than that smaller upper bound. So M has to be the supremum of S. And you could make a similar argument to prove the infimum case. In the next video, we'll discuss some implications of this axiom of completeness. But for now, I'll leave you with a few exercises. See if you can find the infimum and supremum of each of these three sets.